I'm going to be trying to explain to you what bits are for, how bits are used, what you can hold in a bit. Then I'll be explaining how you can use bits and more complicated types to design a file format. And then we'll be going into the fun part, which is looking at a file format that we haven't had documentation for, but we have actual files, and we'll do the opposite. We'll figure out from the bits and the bytes in it what it actually means and how to read them, and then how to verify what we are doing is correct. But let's get started with what actually bits are. For example, if I have this value, what does it mean? I have 4 bits, a couple of ones, a couple of zeros. This doesn't have any meaning. And if I make it longer, it still doesn't have an associated meaning. It could mean a percent. It could mean 108. It could be the number 6.75. It could be 112. It could be 160 kilobits a second at 44.1 kilohertz in some specific context, or it could just be lowercase l. None of these meanings are inherent to the bit pattern. All of these meanings are just meanings that we give to it. It doesn't have an inherent meaning. And everything is just a convention or an agreement on what these specific bits mean. Usually, the convention applies widely. Sometimes it's very local. So what kind of conventions do we have? Well, we have some simple conventions like numbers. We can store a number in the same way we would write down a decimal number. We have 108 in base 10. That's 1 times 10 to the power of 2, which is 100. 0 times 10 to the power of 1, which is 10. And 8 times 10 to the power of 0, which is just 1, which sums to 1 times 100 plus 8 equals 108. Same pattern applies to binary numbers. We can take this binary number, and each of these numbers, based on its location, has a value of 2 to the power of whichever shift location it is. So this number specifically sums up to 2 to the power of 6 plus 2 to the power of 5 plus 2 to the power of 3 and 2 to the power of 2, which incidentally is a convenient sum of 64 and 32 being 96. We're adding the 4, getting to 100, and adding 8 gets us 108 in base 10. So numbers can be stored similar to how we would do this in base 10. So what about negative numbers? And negative numbers are a bit more complicated. They don't just work. So, and the simple idea we could do is just take a number, and instead of having 8 bits being the number representation, use 7 bits for the number representation, and 1 bit to say if it's negative or positive. That works, but it does mean that every time we add 2 numbers, we have to check both of them to see if they're negative, and if so, if one of them is negative, if both are negative, treat them differently somehow, and do some complicated math to get that right. So that's called sign magnitude. And we've by now universally agreed it's not really a good idea, it's actually a pretty bad idea. We've also tried a different method, which is one's complement, which is that if the number is negative, we bit flip all the bits. That means the first bit is set, we recognize it's a negative number, and it almost works easily for mathematics. It just slightly doesn't. It will be off by 1, and we now have a representation for negative 0. Negative 0 is a number that we really don't want to have in math because it would interfere with the number line. So we have 2's complement. And 2's complement is basically the choice that all current computers do. And when I'm saying all current computers, it's pretty much 99.9% plus of all computers being made in the past 30 years. And 2's complement is really hard to explain if you start from its first principles. But if you start from the actual numbers, it's kind of easy. So let's see what we can do. We take the first bit, as with the others, to represent a negative number. But instead of having a kind of method to construct the negative numbers, we're just going to keep subtracting numbers, subtracting 1 every time until we get to negative numbers. And then whatever that representation ends up being will be -1, -5, and so on. So looking at number encoding, this is a 4-bit number. It has 15 possible values. And looking from the left going up, we have 0 through 7. These are all the ones with the top bit 0. On the right, we have 8 through 15, all with the top bit set to 1. The idea is that if we keep counting, we add 1, and we go up 1 in the line. We get to 7, we do that one more time, it flips over to be 8, having a 1 bit in the first place and 0 bits for the rest. We keep doing that again, we get to 15. When we add 1 to 15, we would get 16 decimally. But in this case, we only have 4 bits to store. So it would change to 4 zeros, and the 1 in front of it, the 1 has no place to go, so it's lost. Which means you wrap around back to 0. What happens if we make these numbers negative? And we, instead of counting up from 7, we count down from 0. Then we count down from 0, flip around, and get to the place where 15 used to be, and that's now -1. We subtracted 1 from 0, so it's -1. And we can keep doing that all the way down to find out what the maximum number is. And now we get from -8 to +7. And this looks like a bit of a silly way to do things. Converting numbers from positive to negative, it's not as trivial as it looks, and is a lot harder than one's complement and sign magnitude. But if I do mathematics, it's so much easier. I can just add numbers and not even know if they're signed or unsigned. So as an example, I've taken a part of the table from -4 to +3, and we're adding 3 and -3. In this case, we know they're signed numbers, but we don't really care for addition. We just add them up. So 3 in the binary format being like that, plus -3, which would be equivalent to the number 13 if it were unsigned, but in this case it's signed, sum up to what in unsigned would be 16. Wraps around to 0, which means the 3 and -3 sum up to 0. And there's no special logic needed to do this. This just appears out of thin air. So this is a pretty good convention for negative numbers. But we have more things we want to store. We want to store numbers with decimals. Like decimal numbers would have decimals, binary numbers would have like binaries, I guess. The name isn't used much, but it's the same idea. So in this case, if we have a number with a dot in between, we can use that as a decimal number in the same way you had a regular number. We have 7 times 10 to the power of -1 and 5 times 10 to the power of -2 to indicate that we have fractions of a whole number. Same thing applies for binary. If we have a 1 at the first place after a dot, it becomes a half. If we have a second place, it becomes a quarter, and so on. And that means we can represent partial numbers in just the same way that we did our regular numbers. So what about text? And text is a bit complicated. Because for text, we've tried to do that since the early beginning of computers. And we had some encodings called EBCDIC, which map directly into punch cards. And the mappings aren't as easy as they could be for computers to handle. They were made to be easy for punch cards. So they have accommodations so you don't punch 2 holes in adjacent spaces and rip your card. That's not a problem we have with bits. Bits don't tear. So we have a new encoding, which is called ASCII. And ASCII is a great encoding if and only if you're just using the English alphabet. If you want to write directions to go to a cafe, even in English, you'll have trouble because there's no A with an accent. And we have other encodings that try to go beyond this, and initially they started with identical sized units. So how does this work? So we have a giant string of bits, and we have a convention that we split on every 8th bit. We chunk those up, and we get a number of encoded bits, like this. And for these, we have a convention, again, which is in ASCII, that says the first 2 bits identify roughly what kind of a thing it is. If it's a 0, 1, it's a letter. The next bit will then, if it's a letter, indicate if it's upper or lowercase. If it's a 0, it's uppercase. If it's a 1, it's lowercase. The next 5 bits tell us which character it is. And these are just in the order of the alphabet. Again, the English alphabet. So if we have the first one starting with 0, 1 for a letter, 0 for uppercase, and then the number 8, that represents the 8th letter from the alphabet in uppercase, which is a capital H. Similarly, for the rest, we can decode which of the letters it is, and by knowing the alphabet, we can decode that this says hello. What if we want to store bigger numbers? So far, we had small numbers. We had up to 15 if we were lucky, 7 if we're doing signed numbers, but maybe the numbers we're doing are bigger, like the number of people in the room, or even worse, the number of people going to watch this online. That's going to take a bit more than just 8 bits. And there are 2 conventions for how to do this. Everybody so far has accepted that we put things in bytes, but how to translate from bigger numbers to bytes is something that people universally disagree on. Almost half of the planet wants to use little endian, we start from the little end, which means that we start with the last 8 bits, then the ones before it, then the ones before that. And almost half the planet wants to use big endian, which starts at the front, taking 8 bits, then the next, and then the next. If you're doing this in code, just use a library to do this for you. This is no fun to do in your code, and any kind of shortcut you try to take is going to break in some kind of detailed way. Starting in C++20, we have std_endian, which has 3 enumeration values, one called big, one called little, and one called native, which then either maps to big or little, depending on which platform you're on. You can use this to make your own, but there are enough libraries that do this for you. So we had a couple of things we can do with 8 bits. And so far, they've been encoding simple things. But what else can we do with 8 bits? Well, you can make a lookup table and just map to 256 arbitrary things. You could make them index into a record table for which person it is, which person lives in a village, and so on. You can use them to make variable length encodings, which means you start with a small number, and if the number is bigger than a certain threshold, you will add a second byte to it to have more bits to encode a bigger number. Repeating that, you can make a number arbitrarily large and still know how to store and read it. We can use run length encoding, which is instead of storing all the values, if we have prior information that things are going to be repeating, we can do something smarter. And we can use back references, which is an even smarter way to store things. We'll get into that in detail in just a bit. Let's first try some variable length encoding. And this is one of the first bits of tech from the presentation that isn't going to be trivial and is probably not been taught in school. This is the way that works in Protobuf. So if I'm trying to store the number 1 is a small number, I just store it in a single byte. If I have a bigger number, the number 2, I can just put it in there. As long as the top bit would not be set, so the number would not be 128 or bigger, nothing special happens, it's just a single byte. Which means we get up to 127, we just have a single byte. If we go beyond this, we have 128. And 128 has a top bit set, which means we can't just put it in a byte and expect it to work because it's going to drag in a second byte and then decode that with the variable length encoding. So how does this work? So every time the top bit is set, we take the byte that we have and add in another one. If that top bit is set, we drag in another one, and so on, until we find a byte that doesn't have it set. In this case, we have 2 bytes. So we take these 2 in, we check that the second one doesn't have a top bit set, and then we reorder them back to front. So this is, mentally, you could think of it as a little endian encoding of sorts. We swap them around, so now they're in the right order for all the other bits. And these top bits have done their use, so we need to drop them. Now we basically have the number to read in binary format. We just like to reformat it a bit so it's easier to read. We like to format things by nibbles, which are 4-bit clumps. And this translates easily into a hex number, which is hex 80, decimal 128. And we could do this for arbitrarily big numbers, like having a giant encoding, in this case 3 bytes, take all the values, swap them around, drop the top bits, pack it together, we get 69,420. So this is how Protobuf encodes numbers. Let's go into a bit more detail in Protobuf. Protobuf is a storage library, a serialization library that is used widely. So it's useful to be able to read some of this. So what this does is it uses an expanding encoding for values, the one we just saw, and otherwise it uses serialized structs. Every field is serialized individually with a single value being sent up front saying which kind of thing it is and which of how it's stored, and then the actual value after it. So let's have one. So we have a message. This is what Protobuf calls a struct. It has 3 fields, one of which is the name, the second is an ID, the third is an email. 2 of these are of a type string, which is a sequence of bytes. It's similar to the ASCII one we saw before. And we have a 32-bit int. And the 32-bit int in this case indicates that it's a variable-sized int, and we think we should limit the values up to 32 bits. So we won't be accepting them at runtime, but the encoding could accommodate bigger ones. And in binary, it looks like this. Now, this isn't intuitive. This doesn't look like something that you can just read. But if you know how the encoding works, if you know the convention, you can take the bytes and individually mark them by what they're doing. So let's do that. So we know the first byte of each sequence is indicating what kind of thing it is and how it's encoded. For the values, we take the last 3 bits, and these are the encoding of what kind of format is being sent in. So for the first one, it's a 2. For the second one, it's a 0. For the third one, it's a 2 again. The rest of this identifies which value it is, which of the initial values we have in a struct is being encoded. And these decode to 1, 2, and 3. So we have each of these values present once, and they are being sent along. Now, if we want to read them, we will have to decode what comes after it. In case of wire type 0, that would be a variable-sized int. We know how to decode that now. So we take all the bytes until we hit one that has a top bit not set, concatenate them, flip the order, drop the top bits, we have a number. In this case, it's easy. There is no top bit. We just take the first byte, and that's the value we want. It's 2a, the decimal number 42. The other 2 were strings, and strings aren't stored like numbers. In this case, we know that the wire type 2 is indicating that it's going to be a sequence of bytes. And the wire type doesn't say what the bytes mean, it just says there's going to be a bunch of bytes. So we have a number, similar to the one we had in the wire type 0, that indicates how many bytes there will be. In this case, both of these are a simple number. They're just, they have a top bit that is not set. We can read a 5, there's going to be 5 bytes, which means we take the next 5 bytes. This is the value of the first string. We take the 11, 17 decimal, and we can read this as the final string. So now looking at the bytes, we can figure out exactly what's in here. We can understand what it means, and we can take this sequence of bytes and actually sequence of bits and understand it as a high-level construct, which means that we now know exactly what we're trying to send. So that gets you to the next question. We're sending data, and as we've seen in the Protobuf example, if we're sending strings, it feels inefficient. For every letter in the string, we're saying this is a letter. It is in uppercase or lowercase, and we're repeating a whole lot of information. Maybe we could just do something more efficient. And for this, I'm going to need your help, because compression, it's a bit of an ungraspable topic until you realize yourself that compression is actually possible. So if we take random bytes and random inputs, there is nothing we can do to compress this down. There's no repetition, there's no predictability. But people, and most of the data we produce, is very predictable. So for the next slide, just shout out loud if you know what comes next. So, fourscore and. Fourscore and 7 years ago. I have a dream. Once. Tom and. Game. Supercali. Yes. I love it. It's worked every time so far. So compression works by taking the things that we have already written and then seeing if we can predict what comes next. And if we can predict what comes next, there's no need to store. We'll just say, it is what you expect it to be, like a single bit saying, yeah, it's that. If it's not that, we'll write it out by saying a single bit saying, it's not the thing you expect it to be, and then the rest of the data. So in theory, you can compress anything, but you can't compress things infinitely. And there are 2 ways of looking at this. The first one is called Shannon entropy, which takes a top-down approach of saying, we take the things that we have and we see how much actual data is in this. And we define this as the 2 log of the actual number of bits we would need to store this if we could do so perfectly optimally. So for English text, Claude Shannon came to about 2.6 bits per character of text. That's a lot less than the 8 we're using in ASCII. It's about the same in Unicode, in UTF-8. But it's quite a bit more compact. But that's not the best we can do. As we just saw before, sometimes we're referring to the same text over and over again. And we could be much more efficient. So there's a second definition of complexity in compression, which is a Kolmogorov complexity. This takes the same idea from the other side. We're starting with the complexity of something, by saying what would be the smallest program we could have that reproduces this. So we are taking an output data and we are trying to find out how efficiently could you make a program that does this, and then the size of your program is how big that is. For an example, I recommend to take a look at the demo scene. The demo scene is people that try to make graphical showcases, and some of them try to make them as compact as possible, which means that they will have a 3-minute demonstration, full visual, audio, animation, 3D graphics, really good detail, chromatic aberrations, music, all of that mixed together, and the executable doesn't just fit on a floppy. You could take the entire presentation of all the people doing these things, put all of them on a single floppy. They're that compact. So from Kolmogorov complexity out, those would be really tiny. If you take the Shannon I'm gonna have to cheat, Shannon entropy, they would actually be relatively big because the graphical output is really complicated and trying to compress that down is gonna be fairly large. So we have some general compression techniques and we'll try to go quickly over a few of them. We're not doing all of them. They can go quite complicated to compress better, but we'll just give a bit of an introduction. So we have the general approach, all invented in the 70s by two people who knew a lot, Lempel and Ziff. And they invented two different, but in the end proven identical ways of encoding data. The first one is, we take the data we have, we see if we can get some identifiers from it, some words, we make a dictionary out of that, and then we write out the dictionary and the values that we use from the dictionary. So it's like taking your text, making a dictionary of all the words, and just writing which of the words you're using. And typically the number of words you're using is much less than the actual complexity of what you're writing. There's a variation on this, Lempel-Ziff Welsh, which is used in the GIF image format. And it tries to build the dictionary as you go along, trying to compress images that way. And that was used on the internet for the past 30 years. A simpler way of doing things is run length encoding. This is going for some kinds of data. When you're writing it out, you notice that you're actually writing the same value a lot of times. For example, if you're encoding a cartoon character, every pixel in its face is going to be the same value. There's back reference encoding. It is trying to do the same kind of thing that run length encoding does, but smarter. There's data transforms. These are not compression methods by themselves. These are taking your data as input and taking your knowledge, applying those to make the data more compressible. For example, having a table of names and ages, addresses, and emails. If I put them in that order, it's going to be hard to see the similarity between things. If I flip it around and first store all the names, all the ages, all the email addresses, your compression algorithm is very likely going to notice that all these email addresses have an Atkinson in it. And many of those will end with @Gmail or @Hotmail, and it will compress those by saying, yeah, it's the @Gmail, it's the @Gmail, it's @Hotmail, and so on. So these things are part of a compression scheme. And then we have variable length codes, and we'll be running through an example, running in terms of slide count. So run length encoding, just to give you a visual idea of how compact things could be. Suppose you're sitting on the roadside and you're counting vehicles passing by. We tend to use a scheme like the one on the left. I'm putting a mark down every time somebody passes. If I have 3, I have 3 marks. If I have 4, I have 4 marks. When I get to 5, I will cross it off, so it's easier to count. Which means that if I have 2 of those blocks and a single, that's 11. If I have 80 of them, that block on the left is going to be pretty big already. But writing it out as a number, just 80, is going to be a whole lot more compact. Now, if we have 6,243 cars passing by, I will be using a whole bunch of pages to write all the marks down. But writing down the number is a whole lot more compact. So if we're trying to encode this kind of image, we can take a line of pixels all across his body, and all of those will be white. So instead of saying there's a white pixel, there's another white pixel, there's another white pixel, we can say there's going to be a whole bunch of identical pixels. There's going to be 700 of them, and they're white. Then we'll have like 50 pixels. They're all going to be identical. They'll be black. Then we'll have a bunch of blue ones. And writing it down this way is going to be so much more compact. Then we have back-reference encoding. So back-reference encoding is like run-length encoding, but it's more compact, it's more efficient, it's a bit smarter at what it does. So I've taken a bit of text. This is the song text of the song called Baba Yetu. It's from Civilization 4, and it's one of the few soundtracks from computer games that's won a Grammy. So in case you haven't heard this song yet, listen to it. It's actually a really, really good song. And like most songs, it has a lot of repetition. Repetition is what makes songs, it's what gives them their common theme. So if I'm looking at this, and this is Swahili. I don't speak Swahili. Does anybody in the room? Great, we're all on the same level. We have no idea what this says. If you put this through Google Translate, you'll find out it's the Lord's Prayer. It's a nice touch. But I can see a whole lot of repetition. So if I'm trying to mark the bits that I can see that are repeated, that's a lot. And in particular, I can see a whole bunch of large blocks that just could be said, well, take the stuff that we have written just before this and just do that again. If we take just the big blocks, remove those and replace them with a back reference, this is already a whole lot more compact. It's harder to sing because now you need to work out your back references, especially if you take the smaller bits out as well and make those back references. It's going to be a bit harder to figure out. But this is going to be a whole lot more compact to store, and if your computer program can restore that, this allows you to store your song text with less data. Similar for audio, similar for other things. And in this case, we're not just repeating the same value over and over, we can do more complicated patterns. So data transforms. Just touching on this shortly, this is usually done by compression algorithms for you. It is a good thing to know, because if you have information about your data that your compression algorithm doesn't know, you can often increase compressibility by doing this by yourself. So one of the things you tend to do for this is using an array of structs. The example I gave before, where we have a table of names, then a table of ages, and a table of email addresses. That's the array of structs variation, where that's the struct of arrays, apologies. And the array of structs would be the opposite, where we have a single struct in an array that has for one person the name, the age, and the email, then another struct with the age, the name, the age, and the email, and so on. And this tends to compress more. A second option you can do is, if you don't care about order, sort it. Sorted data has small deltas between the numbers, and if you don't care about order, this removes that complexity of what order it happened to be in from your compression algorithm. It can then figure out that actually all these values are increasing. You can apply delta coding. This is one of the things that the PNG format does for you, which says my values are all in increasing order. So instead of storing the value, I will store the first value, and then the second value minus the first, the third value minus the second, the fourth minus the third. And in case you have very incremental data, like a gradient in graphics, or like house numbers, that's going to result in a whole lot of identical values. Which means that now our back reference is going to say, I have a 2, and then I have a whole bunch more 2s in either of these, and that's going to compress a lot more. And there are more complicated ways of doing things, like move to front coding, which is a very general purpose, but harder to explain technique. You could look into it if you're interested. It's one of the bits used in bzip2. Then we have variable length codes. And I've put this one in because I know some people can read this. I cannot. I'm not one of the people that can read Morse code. But this is a variable length code. It is one that has information and has been trying to make that such that letters that appear often are short and letters that appear less often are longer. And this is almost a binary code. To read these, you need the decoding table. And the decoding tables are widely available. This is one of them. If you're trying to decode this, you start at the center. Every time you hear a dit, you go left or up. Every time you hear a da, you go right or down. Which means that if we hear a dit, and a da, we go left, up, left, and down to get a V. And using this approach, using this knowledge, we can decode the entire message. And this is almost a binary message, but it isn't. I have dits and I have das. And that's the thing that everybody thinks Morse code is, but there's more. If you look closely, there are slashes. And the slashes are not a thing you transmit, they're a long pause. Now, why do we have slashes for a long pause? Because we actually also have a short pause. If you're transmitting 2 characters, there's a break between them. You transmit 3 dots, you take a break. You transmit 3 dashes, take a break. And then at some point you take a long break, which means we actually have 3 or 4 different values, 3 or 4 different trits or quits actually being sent. So this is not a binary code. It's not something we can use. We can use binary code, but we'll have to make our own. Morse is not going to work. So what we're trying to do now is, instead of assuming that we take a byte and we decode it into something valuable, we'll take some number of bits. And that's where the complexities start. We don't know how many bits. But we're trying to use shorter values for things that are more likely and long values for things that are less likely. So let's assume that we're trying to encode a sequence that is mapped to some other table of people of who won the lottery. Well, there are 2 outcomes. You won or you didn't. We can encode that in 1 bit. We have 0 for somebody who won the lottery, and we have a 1 for somebody who didn't win the lottery. This is a very compact one. It's not ideal, and it doesn't contain a lot of information because, well, the jackpot is just 1 prize you can win. There are more prizes, there are smaller prizes. And you're more likely to win smaller prizes, or nothing at all, than you are to win the jackpot. So if we expand on this, we can make a tree like this. So now we have a 0, which is the most common case. It's going to be winning nothing. We have the double 1 case, which is semi-less common, but it's still common enough. It's winning a new lottery ticket, for example. And then we have the very uncommon cases, 100, 101. And these are going to represent the cases that are very unlikely. You won the lottery, you won the second prize, you won 100 quid. And now making such a table, it works. But it's manual labor, and it's something we can't automate. So way back in the past, people have been thinking about this. Can we make this automatic somehow? Can we do this for you? And some people did manage to do so. One of the best known ones is Huffman coding. Huffman coding is similar to arithmetic coding and range coding, which are more complicated to explain. So we'll go for the simple one. We'll just do Huffman. The idea of Huffman is you take the values you have, you find out how often they occur. The ones that happen a lot will end up high in the tree. The ones that don't happen a lot will end up lower in the tree. Which means that in this case, we have 36 values, and we sort of split them evenly between the branches. We have 20 on the right, 16 on the left. Then again, we're splitting them over. So 8 on the left, 8 on the right. The left branch will have E's, and we have 4 E's, which means that we're going to the left if we have an E. That's 4 of them. And the right branch will also be occurring 4 times. But that's not a single thing. That's probably going to be multiple things. In this case, we have 2 N's, and in the other branch, we're splitting again to O or U. We can take this, and this, in this case, is actually a binary tree, and we can assign them values. Now, which value we assign to which branch is irrelevant. They could be 0s or 1s. They could be flipped around. In this case, I've gone for the simple one. Left is 0, right is 1. And that gives me an encoding for each of these letters that is a maximum of, in this case, 5 bits. That's a lot better than ASCII was. So let's see if we can get through this. Let's see if we can use this to encode something. Now, encoding this is going to be annoying, because if I want to encode this, I'm going to have to look for my letter, just scan through the bottom and find the letter, and then scan up to the top to find out which of them it was. But we can flip this around and make a table that says if you're trying to encode an E, it's 3 zeros. If you're trying to encode an I, it's going to be a 1 and 3 zeros, and so on. So let's make a table. And now for encoding, and because, well, the screen is full, we'll just hide the table. We'll hide the graph. So we have the word hello. It's a simple word. And in this case, we have the ASCII patterns beneath it. We're not going to be using ASCII, but this is for reference. These are 8 bytes each. Total is 40 bits. Now, if we take an H, we can see that in the left, it maps to 1010. So we're encoded as 1010. Then we have an E, 3 zeros, append that. We have 2 L's. Look up the code, append those. And doing so, we end up with a code that is 22 bits. And that's great. I found a code that is a lot shorter, it's a lot more compact. But the proof is in the pudding. You can invent really short codes for things, but unless you can decode them, they're useless. So let's see if we can do that. Now this is the one that we had, the output. And we've tossed out the table. We're using that for encoding, not decoding. For decoding, the tree is more useful. And we've lost the entire input because we don't want to cheat. We just want to look at this and know that we can read it. So let's put them side by side. Now we're going to start at the top. We take a 1, which means we take a right. Next bit is a 0, we take a left. Next bit's a 1, we take a right. A 0, we take a left. There are no lefts or rights left anymore, which means we have to have matched a character. So in this case, we're saying we matched an H. We put that over there, we have an H. Now we're going to mark this bit, these 4 bits, as something we've already matched. And we're going to go back to the top in the table. And we're going to do the same thing again. Start with a 0, go left. Start with another 0, go left again. Start with another, go left again. We get to an E. We're at the bottom of the tree, and this time we only used 3 bits. Doesn't matter, we'll just accept we had 3 bits. And we matched an E. And we're going to do the same thing again. Right path, getting to this code, which is an L. Match it, go to the next one. Match the same thing, it's an L. Next pattern is going to be an O. It's all the way in the left. And at this point, we're at the end of our encoding. And we have decoded this to mean hello. We have no bits left, which means that we properly decoded this. And indeed, we get the value we thought we were putting in. So even for a very short term, this would already be a lot shorter. So Huffman coding is one of the basic techniques. It's a general purpose technique. It can be used for any kind of data. And there are 2 ways you can use this. One of these is having an implicit table, as in somebody already defined a table for you and put it somewhere on the internet, for example, or in a specification. And to read your data, you need to know what their table is. Given their table, you can read this. It works best if you have some kind of idea of what kind of values you get. So this is used in, for example, JPEG, where the values we get tend to be lots of zeros. So we're encoding zeros very compactly, and everything else is going to be bigger. This saves a lot of space because we don't need to take our table and put that into the file. So in some cases, if we have a reasonably good idea of what the data is, we can just use a table predefined. Inversely, if we don't, we can look at our data and figure out what the table should be, create a table, but then we're going to have to encode the table itself into our output. Output is going to be a bit bigger because we include the table. But the more data we're encoding, the more likely it is that we're still saving space. Then we get to the final bit of the basic intro. We have bytepacking and bitpacking, and this is the general approach. So for bitpacking, like Huffman tables, we're trying to encode things as compactly as possible, but we have nothing to hold on to. We just know there's going to be a bit, there's going to be another bit. In some cases, we can say we have a 4-bit value, we just read 4 bits. And these things are going to be very compact. If you can use bitpacking, it's going to be the best way, but bitpacking is really hard. It's a lot more complicated. And reading it is going to be much more complicated. In particular, some compression algorithms really don't like bitpacked fields, and they're going to do really poorly if you use them. And sometimes we use these mixed. For example, we have a couple of fields like how many bits per second we're transmitting, what kind of frequency we're using, the data. And we just make some predefined things saying we have 4 bits for the first, 2 bits for the second. We take 2 other Boolean values and we just pack it all into a single byte, store that as a byte. And now reading it is a lot more easy. So that's the basics. Do we have any questions so far? Okay. Then we'll go to the second step. Now we have the basics. We're going to be designing a binary file format. So what's the reason why you wouldn't? And why many people are going to say you shouldn't be making binary files at all. You should be using XML, JSON, any kind of arbitrary other way of serializing data. And the first one is endianness. We've touched on it in the beginning. There's big endian, there's little endian. If you mess it up, your data is going to be corrupted. And there typically isn't a whole lot to check that you did the right thing in decoding. In this case, it's easy to handle with libraries. The second one is that some platforms really do not like binary data. They consider things to be text usually, and if you write your code correctly, you can read binary data. But if you mess up somewhere, it's going to try to read it as text and convert your new lines for you. And if you're converting new lines from things that weren't new lines to begin with, that's going to completely mess everything up. In one way, it's recoverable. If they strip out bytes, it's going to be completely unrecoverable. So this used to be a problem. By now, most operating systems have started treating everything as binary files, and this problem is almost disappeared. But it's one to keep in the back of your mind. If you get some corruption, it might just be this. So what kind of binary files do we have? Well, to start with, we have a flat file. And a flat file is, as it says, it just has a dump of data. There's no structure to it. There's no higher level indication to say what kind of data it is. It's just take the data you have, put it in a file, no indication what it's supposed to be. Then there's the next level up. We have our data, like image data, and instead of just dumping bytes into a file and pixels, we're going to be telling it, this is an image. The image is going to be this wide, it's going to be this high, it's going to have this many bits per pixel. Maybe it has a palette, and we're going to put that in there. So this is the kind of file format that we used to have in the early 90s. They have enough information, but they're relatively inefficient. They just have a flat dump of whatever data we have. The next level of file that you could have is one that has a header, and it has multiple bits of information. We try to make an index of them, so you can open the file, read the index, and then find out where your data is. For example, computer games, they would open a file that is multiple megabytes in size, find out what the offset is of the sprite they're trying to display, seek to that offset and just load that sprite instead of the entire 7 megabyte file. You couldn't load 7 megabytes, you only had 4 megabytes of RAM. So they had to do this, and it worked pretty well. The fourth kind of file is a record-based one. And initially, I thought that this was a historic artifact. Records are basically a top-level struct that has a header and some data, followed by another header and some data, and some more, another header and some data, and so on. Turns out, many file formats are still designed like this, like PNG. Chunk file formats are like record-based ones. They have a header and some data, followed by another header and some data, and you can typically take two of them and concatenate them. There's nothing stopping you from that. But chunk files tend to be recursive. You have a chunk, and instead of just being a chunk, it could contain other bits of chunk. And each of these contains a description of what kind of chunk they are, what kind of value they have. So they're a little bit of a higher level, more complicated kind of file format. So we have a flat file. It's a lookup table. A raw palette would be such a thing. You typically find these in really old games, 768-byte files. It's probably a palette. You have raw images. If they're coming from your photo camera, it can usually do raw image storage. And these are going to be without any post-processing done on it. And they're just going to be the raw bytes from the sensor. And in some cases, they won't even have a header saying this is a raw image. It's just going to be bytes. And loading them into graphics tools is going to require you to inform it what kind of resolution it's supposed to be. And if you did that right, it's going to look like an image. If you did it wrong, it's going to look messed up. Close the editor, try again. Hope you got it right this time. So header and flat files, these are a lot more useful already. You can often read them like a flat file if you guess the right values, just by skipping the header. So if you're trying to make some debug code and you want to write out an image, this is the kind of file format that you really want. You can write a WAV file, dump a header, a prefix header that says it's going to be just raw audio, and then take your audio and just dump it in the file. Any file playback will just read the header, assume it's going to be some audio, and play it back. Same for a bitmap. It's going to be some bytes, and these bytes are going to represent an image. And as long as you have the same format every time, for example, your game's resolution, making a debug handler that takes a screenshot and dumps it into a bitmap is a really easy thing to write. We have header, index, and data files. These are usually archive files like a zip file, not a tar file, but zip files. And these are also going to be formats that have basic animations. We have a record sequence. So the record sequences are header and data, followed by another header and some data. This is famously used by the program called tar. And tar is called tar because it was meant as a tape archiver. Tapes are famous for having really long seek times, which means that you want to write some data. You do not want to use a lot of memory because the computers back then didn't have a lot of memory to use. So you want to have a single file, write a header, say it's going to be this long, write the actual data, and then never have to look at that bit again, just concatenate another bit. If you're trying to add to your tape archive, you do not want to load in the entire tape to some other format, then to re-index it and write it all back to tape. That's going to be incredibly inefficient. So one of the features of the format is that you can take the file, seek to the end, and just append another file. That's a benefit in case you're using actual tapes. It hasn't been a benefit in a couple of decades, but the file format still does this. Similarly, the GIF file format also has records. It doesn't actually have the benefits from them, but it does use this kind of format. The PNG format also has these kinds of structures. And in this case, they are usually used so you can add some records that some file formats or some readers don't understand. For example, if you're Apple, you can make your own chunks in here, your own records, and they contain some information about what kind of camera they were taken on, what kind of information was done with them. You can include some extra images, 3 of them to show beforehand, 3 of them to show after. And if you're a different parser, you just see a record that you don't recognize, skip over it, and you still get the image. It's a way to make your file format extensible. And then we have chunked files, and these are, by now, I would say, one of the most common things to see. So for example, Autodesk FBX files. These are a chunked file format. They contain top-level data, and inside this top-level data, there's going to be a bunch of entries saying different kinds of sets of information. There's going to be a bit of information about what kind of image it is. Maybe it's a skeleton. Maybe it's going to be a 3D model. Maybe you have some textures. You can put all of that in a single file, and the chunk header is going to say, this is going to be all the textures. It's going to have a bunch of chunks that are textures, and each of these texture chunks are going to have a chunk saying, this is the header about that, describing the image. This is going to be the full resolution image. This is going to be a half resolution image, and so on. Same thing for Blender. It does the same kind of thing. It uses the same kind of approach. Things like AVI and Matroska, the movie formats, they do the same thing. They have a different reason for it. They're not trying to have different kinds of data that they store in different chunks. They're trying to have different kinds of data stored in a single chunk, followed by another bit of different kind of data in a single chunk. So we get the first 5 seconds of audio and video in the first chunk. Then we get the next 5 seconds of audio and video in the next chunk, and so on and so on. That means we can take the file, start at the front, read through it serially, and while we're doing so, we get the video and the audio pretty much in sync. We don't have to read the video, skip to the end, read the audio, skip to the front, read the video, skip to the end, read the audio, and so on. Again, this is not a big thing if the file's on your hard disk, but if you're streaming from the internet or if you're streaming from a DVD, there are different times when you would do this, but there's the same effect. And like we saw before, Protobuf has a message, and the message has things in it. And these messages can contain other messages. And they also get the same benefit that we had in tar. If you have 2 Protobuf files that are according to the same schema, you can concatenate them and get a file that contains both of those bits of information. These are bits of information that are rarely useful, but the one time, it could be really the big thing for you to save your life. So as soon as we started figuring out what kind of way we want to store our file, the big question is, what are we going to do with it? As we referred to before, maybe I'm going to be streaming this file. It's coming from the internet, it's coming from a sequential medium, a DVD, a tape, and I really need to be able to take some bit of data as it comes in, use it, and toss it out. In case of tar, that was because we didn't want to store it, we didn't have memory. In case of a video, it could be because the rights holder doesn't want us to have more than 20 seconds of decoded video. So in that case, we just have a machine that doesn't have a lot of memory. We read in a bit of information, we decode our video, display the image, and discard all of it, and so on. Sometimes our data is huge. For example, I have a world map, but I only need parts of it because I am not in the US, I'm not in the Netherlands, I'm not in China, I am in the UK. I need the part that's the UK, and specifically the part around Bristol. And we can just not load everything else. That means that my multi-gigabyte, multi-tens of gigabyte file doesn't need to be loadable and I don't need 100 gigabytes in my navigation system, I can make do with a single gigabyte. I just load the bits around me. Sometimes this doesn't apply, because while I can load parts of a world map to navigate someplace, sometimes I need the whole thing to be usable. For example, if I'm looking at an image, there's no way I'm going to be using that without loading the whole image. If I have a 3D model, I can make it very compact and make it so you can just read the skeleton, but you're not going to be using the skeleton. You need the skeleton and the textures and the actual model. And that combination is a usable thing. There's no use for loading parts of that. Very little use, I'll admit. So we need to think about what our use cases are. And in that case, we need to think about, we have our use cases, and which of those are going to be critical. In the case of streaming, we might have to choose for that because we have a low amount of memory. In case of having a server with a giant map, we might have a problem that not the whole map fits in memory. We can only load parts. So we do want it to be efficient, but we do need everything to be accessible. We'll need to page some things in, page some things out. And most of the time, this is talking about a working set. And the concept of a working set is one, it translates really well to a really nice metaphor. So there's a thing called AFOL. Does anybody know that acronym? It's an adult fan of Lego. These are basically the people who are now 40s, 50s. They like playing with Legos. And Lego has a working set. If you're trying to build a model, you can start from your Lego set. This is a giant pile of Legos that somebody's at some point collected. And building a single model in this is going to be hard. You have a giant working set to find parts in, which means that you're going to have a lot of memory where everything is, which parts you need to find. And if you're trying to find something, you're going to have to dig through it to get the right bit. And Lego themselves have realized that even for big sets, this is a big problem. If you get the whole set, all 6,000, 9,000, 10,000 pieces, yes, they do come that size now, it's going to be really hard to build. So what you do, instead of having a giant box that contains all the parts, we have numbered bags that contain incremental bits. So we have bag 3, 4, 5, and 6. And you're going to be incrementally building it, and this reduces your working set to just bag 3. And bag 3 is going to be nice to find the parts, but as you're building, it would be nice to know the working set for that page. So by now, Lego's even gotten to the point that they are printing for each instruction exactly which items you'll need to find, so you can then take a smaller working set and build that incrementally. So this is a metaphor for what a working set is and why you would care. So in many cases, we want to have a working set that is as small as we can make it, and at the same time as useful as we can make it. Computers are really slow in reading things, especially the further it's away, the slower it's going to be to read. And the more we can use our local caches, the faster things are going to run. That also means that if we are able to store things more efficiently in a cache, it is also going to be faster. If I'm reading things from disk and I need to load 1,000 pages to get 1,000 bytes of information, that's relatively inefficient. I'll need to read 4 megabytes of data to get 1,000 bytes. If I put that in a different order and take those 1,000 bytes and put them in a single page, now my disk only needs to read a single page, and I still get the same amount of effort. Similarly, the more efficient you're doing, the more efficient you're packing things into cache lines and keeping track of what cache sizes you have, the faster your program is going to be because the effective cache size is going to be a whole lot bigger. And caching isn't just a thing we call cache. There's a level 1 cache, there's a level 2 cache, there's a level 3 cache. There's main memory, which also functions like a cache for your disk. Your disk functions like a cache for the whole internet. You can download files, you can throw them away, you can re-download them. And every time you go back a step, it's going to be a whole lot slower. Your CPU has registers. These can be accessed in a fraction of a clock cycle. That's going to be a fraction of a nanosecond. If you go to level 1 cache, it's going to be a couple of tens of nanoseconds. If you go to level 3 cache, it's going to almost approach a microsecond. If you're paging to main memory, it's going to be even slower. If you're paging to disk, it's going to be a 4 kilobyte load, because storing anything smaller would just be silly. The overhead is so large that the data size is almost irrelevant at 4 kilobytes. And even 4 kilobytes is nowadays kind of silly. Many systems are starting to switch to 16 kilobyte pages just because 4 kilobytes is so tiny and so little that the overhead is starting to dominate the actual loading. And in worst case, you can stretch that all the way to the internet, where you could say, well, I have this file, and I'm not going to need it, but I'll make a hook in my file system that if you do use it, it'll just re-download it. But it could take a couple of hours. Talk about latency. So we have use cases. We also have the logical use cases. We don't just have how efficient things need to be, we have the how are we intending to use this? So take, for example, a video file. If I'm looking at a movie, I will take the movie, start at first, go usually all the way to the back. Maybe I'll at some point index, try to find out where I left off yesterday evening, go to one point and watch to the end. I want my file format to be such that it does this efficiently. So audio and video should be interleaved, the subtitles should be available there, and there is no point to include any other information like a really efficient seek table or the ability to play the movie backwards. Now, if I'm video editing, this is useful because I'm going to be scrubbing through the file. Scrubbing is the act of finding a location in a video file. And while I'm trying to run through it to find the right place, I do need all the video images. So I don't just need the ones every 3 seconds to be visible. I would like to just be able to scrub to write the exact image that I'm looking for. Maybe there's a moment that a ball hits a table. I need that exact image. So I might have a second stream in the same file that says these are the smaller sized images, and you can decode each of these individually. And then we have the large scale information that is played sequentially. Then while I'm editing, I'll take the smaller resolution bits, do my editing, be quick, and when I'm rendering the final file, I'll take the full resolution stuff, render it front to back, not be bothered by it being slow to read, and next morning, everything is rendered in high resolution. So based on the way you're trying to use something, you design a different kind of file format, even if it's the same data. The second step is trying to find out what kind of stuff you're storing. And this is much harder than it seems to many people. We're trying to find out which things we have. What kind of relationships are between the things? What kind of multiplicities do we have? How many of something do we have per something else? Can I assume that somebody has one address? Do they have two? Do they have a number of them? If you're going to work, is that one location? Or do you have a sequence of work locations? Maybe your work location is at home. Is that a thing we need to support? Is your last name 2 characters? 1 character? Maybe you don't have a last name? What about middle names? If I'm in the US, one of the common questions is fill in your first name, your middle name, and your last name. If you're not from the US, you might not have any idea what a middle name is, or you might have 10 of them. These forms don't expect this. They are modeled on the US. And the modeling doesn't take into account some of these variations. So as soon as you figured out what kind of data model you have, try to find out how can we use this information? How does this information map to what we're trying to do? Do we take this data and put it into some kind of a group? Like, for example, if I have the locations you are often going to, it's probably a good idea to bundle those for a user, instead of bundling those per location for the users that happen to have access to that location. It's going to be a much less useful format if you make those choices backwards. You're also going to be thinking about what kind of an index do I need. If I'm looking at the UK and I'm trying to go to a Boots, a pharmacy, I would like to be able to type in Boots and have a search index say, these are the locations of all the Bootses. And I would like that to be fast. I don't want to type it in, wait for half a minute, and then get a list of the ones that are relevant. So I might need to index that information. For example, all the things that start with B go into one index. Or all the pharmacies go into one index. Or all the things near Bristol go into one index. And depending on your use case, one of these might be better than the other. If you're trying to index things around Bristol, the second one is the most useful. But if you're trying to find a pharmacy, you're not helped by the one that indexes by the letters. So think about what kind of an index you need, which one would help, and which ones you can make, but they're not going to help anybody. Then we're going to be taking our data and we're going to be grouping them. We start by having basically an idea of how we represent things in the file, and we know we have caching, we know we have working sets. If we can group things in such a way that our pages are going to contain relevant information, we will load fewer pages to load more effective data. So trying to group things bottom up, things that we are typically using together, things that belong together, and we're going to be indexing top down. So from the top, we know which things we have in the entire file, and we want to make it so you can find the right thing without loading the rest of the file. You could make all your locations into a giant list, just load the whole file and scan through the entire list. If you do that on an embedded platform, you're going to be waiting for minutes. Inversely, if you have a good index, you can load the index, find the right entries, find the right bits of file to load, and be a whole lot quicker at getting the same question answered. And your file format is going to be better for it. Then we create our specific file format. So we start with knowing which things we have. We are now trying to make them into actual structs. We're trying to pick some library that does the serialization for us, or we're going to write our own. Used to be more common. Nowadays we have Avro, we have Protobuf, we have Thrift, we have probably 20 more libraries that can do this for us. And these are going to be really efficient if you're designing your own file format. They're hard to retrofit onto an existing file format, but usually these allow you to really compactly define some kind of structural composition, and then being able to write that out into a file. And in some cases, you still want to create your own abstraction. These things are good at storing general data in a not very indexed way. As soon as you need to make an index, try to figure out a way to make that happen, but you're going to be going around these libraries at that point. And we're going to be preferring optimized data structures over just reusing the same code again. So again, if we have an index, we can use B+ trees, we can use radix trees. We have different kinds of algorithms that we can run, and we can use data structures that match those that are going to make for very efficient access. We use these, we make them appear in the file somehow, we write them to disk, and loading them from file should be relatively easy to do. We take the index, we map it into memory, we use these structures with whatever software we have for them, and we're trying not to transform them too much. Then we have the final bits of making a file format. If you have a file format, the first thing you're going to do is make a file format that has a specification. And the next thing that's going to happen is somebody's going to come to you and say, I have your specification, but it doesn't work. Oh, right, we checked in a change yesterday evening, and we actually swapped these two fields. So now if you're going to read with the old reader or the old spec, it's going to be backwards. Right, that's not going to work. Somebody else is going to come to you and say, I have this file, and it has a video, and it doesn't load with your library. Well, yes, but it's not using my file format at all. But there's no way to know it wasn't my file format because I didn't put anything in. So common solutions are to use some kind of a header at the start saying, this is the kind of file format. Use a magic value. It doesn't matter what the value is, just make sure it's some kind of random thing that nobody else is using yet. Make a best guess, do your best at doing it right. If you do collide, that just happens. And the second bit is always take into account you will need versioning. Even if it is just you looking at your own file created last week and wondering why it doesn't work, you will need versioning, and having it blow up when it loads the file saying this is the version from last week, I am not going to read this, is saving you weeks of debugging, figuring out why this thing is backwards. Then we have the big endian and little endian question, and this should not be a question you need an answer to. Your library should do this for you. This should not be a question. The only case this is going to be a problem is if you have a direct mapped format. If you're memory mapping, and in C++ terms, reinterpret casting that data to be a struct, which means you're assuming everything is going to be your native endianness. That works, it's fast, it's very quick to write, and it's going to mess up a couple of times. Try not to unless you really have to for performance. And the best option is that instead of taking your file, memory mapping it, and then casting it to some kind of a structure pointer, instead make a view type. A view type is a thing that takes the same span of bytes, but instead of having direct access to it, it takes a library abstraction to read from that. It doesn't copy data, it just interprets it for you. And in that case, you don't need to know the endianness. Your view type does this for you, and it will be almost as fast or exactly as fast as direct access would be. So now we're ready to wrap up. We take our file format, document it, make some kind of library for people to read it and write it. So we're trying to be able to read it efficiently. If it's a mapped file format, we're going to want to memory map it in or load it in. Typically, you want to map because that's going to be faster. You want to check the file, at least check the header to see that it's the right magic value, it's the right version, or it's a version you know, and load the indexes to be able to find things in the file. Then we're going to try to provide some kind of view-style access to the index. So we don't want to provide somebody with the raw data in the index. We want to provide somebody with the operations on the index you're trying to do. You're trying to find a pharmacy. It gives you an interface to find the pharmacies. It doesn't need to know how you're storing pharmacies. It just needs to be able to find the pharmacies with your index. And sometimes you'll be wanting to add some caching. For example, if you have the long tail style data access pattern, which means you have a couple of things that many people use, and you have a lot of things that very few people want, but it is important you have them. For example, Amazon's list of books that they have. There are going to be bestsellers, millions of people will buy these, and there are going to be the obscure books, like how to make a floating points emulator. And only 10 people in the world are going to ever look for that. If you want to efficiently do this, you want to cache the long tail bits, and you want to have the rest of them loaded. And the cache is going to be your way of doing that. And then we have our first version. We take our first version, deploy it on a target, figure out how well it works. Does it work well? Does it not work well? Which kind of use case did we anticipate, but did we just do badly? Is there a better way of doing things? Maybe this view type is too inefficient. We'll need to go for directly mapped. Inversely, maybe it's fast enough to just use a view type. Maybe my index is a B tree and a radix tree would be much better. So create variations of your own implementation. Try to find out which bits of the file format work well, which bits don't. And don't lock yourself into whatever you designed first time. And more specifically, check on your target hardware. What might work well on your computer could work really badly if you're running it on the embedded platform. It might have much less memory. Its caches might be much less efficient, or maybe the inverse. Your computer has a really big cache, but it's slow, and your device has a really fast cache. Either of these could be true. Check it on the actual platform and see what you can do. And then we get back to the previous point. Now we have multiple versions. So how do we deal with multiple versions of our file format? The simple answer is we just support the latest. If it's not the latest, we blow up. We tell the user, sorry, your data is gone forever. Users get mad. So we need to find a way to deal with our format is now in the field. We're still iterating on the design. We have some newer formats. Maybe the field in this case is your colleague's desk. Maybe the field is somewhere near Venus. They might be updatable. They might be hard to update. One of the things you can do is make multiple versions of your reader. Whenever you change the version, make a copy of the entire reader program, the entire library, make a version 2. It's going to duplicate a lot of code, but you are free to change anything you like. And it's going to work backwards compatible with either of them. Inversely, you can say my new version is going to be the old version with a minor tweak. And if you do this, you're going to be creating a single one and have a couple of if statements. As you go on and iterate more, you will have more and more of these. And as far as I can tell, this always ends up being a giant ball of spaghetti with a huge amount of if statements and combinations of features that never actually happened. But in the spec, it's possible. So you'll have to find out a way to deal with it or just abort and hope that nobody ever figures out. So what about making a backwards compatible kind of reader? So we make a single reader. It has conditionals to handle all bits of format. And we try to add the things that we're trying to add in an incremental way. We're having new fields. Some of the new fields replace old ones. Some of them add on to old ones. For example, if we have a bitmap, and the bitmap could at most be 255 bytes wide, 255 pixels wide, and then we have an upgrade to that. We add a second header that we could call the extended header. And it has a 16-bit field for the image width. And now, if that thing is there, that field takes precedence. If not, it's the old one. Or, if the value is too big, it will be in the new header. If it would fit in the old one, it will be in the old one. And these are ways to approach this. Of course, you're going to find out that the value you made bigger in 20 years is going to be too small, and you're going to need to do the same thing again. But this is a thing you'll find in a whole lot of file formats that have survived multiple decades. So for example, the ELF executable, it used to use 32-bit offsets for everything. And in some cases, that proved not to be big enough. So now there are some patches onto it, some additional headers, that replace values in the old one if it's too big. And in some cases, we can even make it better than that. We can make things that are backwards and forwards compatible. This is a thing that Blender is trying to do. It has a file format that describes what data is in it. And as long as you know what to do with the format, you know what to do with the data, you can use an old version of Blender to read a new file. If it's not using any of the new bits, they're going to be in the file, but you're just going to skip over them and ignore them. If you're using a new version of Blender on an old file, it's going to read all the old structs and convert them for you to the new format. And if you save a new one, it's going to be in the new format with everything a bit more optimal. It's a really nice idea, but it takes a lot of work to actually make work. Similarly, Protobuf, as you saw in the example, you have optionals, you have repeated fields. And these could appear in the data, which means if you want to replace a field with a bigger field, you want to replace your 32-bit int with a 64-bit int because somehow there are more than 4 billion people, you can do that. You can add a new field that's called int64 for a certain ID. And in case of Protobuf specifically, it's a variable-sized int. We can just upgrade the type. And if the number happens to be too big, the old library will complain, saying, well, we have more than 4 billion people. This is now going to crash because the old code can't handle it, but the file format is still exactly the same. So some of these things you can just handle in your libraries. And then we have the last one. If you're making a file format, you're going to be spending a lot of effort on it. And there's 2 things you can pick out of these 3. You can try to do it as cheap as you want, and it's going to be compact or fast, but it's not going to be both. You can spend a lot of effort on it and make a really generic file format that's going to be compact and fast, but you're going to be spending a lot of effort. And time is money. You're going to be costing a lot of money there. You can make something that's compact and cheap using general compression and compressing everything down as much as possible, but that's going to slow everything down. So figure out which of these 3 you can leave out, and it's usually not going to be cheap. So figure out which one is more important and go for that. And that brings me to the final point of the talk. We're going to be reverse engineering. So has anybody been reverse engineering before? That's good. So if you were bored in the basics, this is going to be fast. We're going to be reverse engineering a file format. And the thing I like to reverse engineer mostly is the kind of thing that doesn't land you in legal trouble. Practically, it doesn't land you in legal trouble, so I'm happy to present it on stage. But also, it's usually going to be the kind of thing that people never expected others to want to read now. So no effort was made to make it readable. But other than it not practically being readable, there's no reason why people wouldn't want you to read it. So in many cases, this is just old software. Somebody used to have a file format designed for whatever reason, and it just happens to no longer be readable. And this happens a lot in computer games. Because a computer game makes its own custom format, it encodes everything, everything runs, game is done after 3 years, nobody looks at it anymore. Guess we're done. The files are unreadable, the game is unplayable. The game assumes that you're needing Windows 95 or maybe 98. My Windows doesn't do 98. It doesn't even do the Windows part anymore. In many cases, because it used to think Windows was 16-bit, and the new versions of Windows are just going to say, well, no, that doesn't exist anymore. So the games don't run anymore. If you want to make an open source version of the game, you're going to need to read the files. The files contain almost everything. The game engines tend to be very generic, and they try not to have anything hard-coded for the game. They will, in case there's a last-minute hack and something just falls through the floor, and you're just going to say, well, if you're in that location, then don't fall through the floor. But in general, they try to have as little of the game in the executable as they can. So we're going to take this game. Does it ring a bell? It's been a while. It's 93. And it looks like this. It was one of the first games that tried to use 640 by 480 images. It was very high resolution, back when that was high resolution. It did destructible terrain. It did a whole lot of nice things. And I have a whole lot of nice memories from it. Main reason being, this game is the reason I'm doing C++. For some odd reason, I got a debug build of it. I still have no idea how that happened. And it had asserts enabled. For a second reason, this is the exact time when CPUs started to get to the point that they couldn't be ambiently cooled without a cooler anymore. But no sockets included anything for attaching a cooler. So you had these clips on the side of a cooler that were meant to go over the CPU itself to hold it on. And while I was playing the game, you know what happens? It fell off. I had a tower, which means that when it fell off, it fell physically onto the floor, and nothing was cooling my CPU. Now, this is the early days of CPUs needing cooling, so they need cooling, but not all that much. They'll be fine for a couple of minutes, and then they'll start making some mistakes. So I noticed when I was playing the game, it would crash after 5 minutes, reboot, crash after 4 minutes, reboot, crash after 3 minutes, turn off the computer, go do something else for an hour, get back to it, crash after 5 minutes. I know what this is. Unscrewed the case. Yep, it's lying on the floor. It's not cooling anything. Let me take a glue stick and just stick it on. Worked fine for the whole weekend. So in the end, that game kept crashing. And I noticed that it was crashing and indicating there's an assert failing in this line on some kind of CPP code. And me being like 13 was like, you can make this with C++? I gotta get me some of that. So I went into C++, and long story short, here we are. So let's get into it. The first step when you're reverse engineering is always go see if somebody else did. Because you're not the only person with this kind of interest. There's gonna be a bunch of people who do this. And if you're searching for an hour and find somebody who did everything already, it's gonna save you a month of work. But where's the fun in that? So we're just gonna do it anyway. Incidentally, nobody had done this before when I made the talk. At this point, somebody did re-implement it into ScumVM, so there is a new playable version of it. ScumVM now has an implementation that mostly works. Ultima 8, which is the predecessor to this game, is mostly documented and is pretty well documented, and Crusader isn't. But most of the documentation somewhat matches. You can at least get some ideas from it. So I used both of these as an input, and for the rest, just tried to figure out what I was doing. So step one, we're trying to find out what the files are. We just use the simplest tool we have. It's called file. It tells us what kind of file something is, or at least it's going to try. And in some cases, it's going to be perfectly spot on. It has a whole bunch of DAT files. Turns out these are bitmaps. What can we do with a bitmap? We can just show it. This is the first one. It's the backgrounds of credits. Second and third, these are the help items. And as far as I could tell, these were all the ones that I saw in-game as a bitmap somewhere being presented. But these are 3 images. And there are 4. I have credits, which is the credits. I have help 1 and 2, which is the 2 help screens. And I have help 3. There is no third help screen. Turns out, there are Easter eggs. This is one of the developers, who's now not so proud of having this image out in the open 25 years after he made it, but, well, it happens. So, second bit, we have a fix.dat. And the file tells me it's a DIY thermocam raw data file with a temperature of absolute 0 and a negative scale. I don't think that's right. These are data. In case you hadn't guessed, data is data. That's not helping. Okay, second step. We take the files that we have and the ones we haven't figured out yet, like the credits and the help. We try to guess what it could be. So gamepal.pal. I'm guessing this is a game palette. We have shapes.flx. Well, shapes used to be a name referring to sprites that are animated, so I'm guessing, probably fine. Type info. Info about types. Starting to get a bit generic here. Trig.dat. Trigonometry. Turns out we used to have a really slow sine and cosine, so they made tables for it and loaded them. These are those tables. Yeah, we can do that. Combat, damage, and D table. Combat information, data, damage information, and damage table. Sounds okay, it's probably that. Use code. That's a data file with code. That's interesting. It's going to be a hard one to figure out. Globs. We got globs and gumps and fixed and, you know, stuff. Yeah. That's going to be hard. Okay, step 2.5. We still have the same files, and file isn't doing it, the names aren't doing it. We'll use strings to find out what stuff is in here. And that helps for use code. It has almost all the in-game strings, all the message boxes you get, the information you're getting told, a whole lot of stuff like that. And the rest of it feels like executable code. So in terms of reverse engineering, that's going to be a hard one. But I guess we're going to have to bite the bullet at some point. It's not x86. It doesn't even look like it. It's an in-game VM of some sort. And looking at Ultima 8, it has use code as well. It does probably the same thing. Gonna hope it's going to be close. Credits of that has the endgame credits. So it's just text. Yeah, you can read that. It's interesting. Not that much. Step 3. We take a file, and we are just going to hard code, trying to get through it and figure out what it is. So if you were wondering where the hexams are, here they are. We're going to be looking at it and trying to find out, is there a header? Is there some kind of an index into what the rest of this is? Typically, files will have indexes, unless it's chunked or record-based, but we're hoping we don't get these. If they are record-based, maybe they're fixed size, maybe they're size prefixed. These are common things. End of the story is, somehow the software needed to read this, and they're trying not to put everything in the executable, which means that it has to be in the file somehow. You have to be able to read the file with the file. So looking at this, does anything jump out at you? 32 on the last line. You have a 32. That's an ASCII code. That is something that jumps out. The thing that jumps out to me is there's a whole bunch of bytes that are not 0 that are the same. What is that? I'm going to be interested if you're right, because I have no idea what they are even now. But I do see this, and I see these values. And to me, these look like little endian values. They seem to be some kind of a big value, starting with 6080, which is slightly over 24,000 bytes, and a small value. A big value, a little bit bigger than that one, like that much bigger, and another small value. Another value that's bigger than this one by that amount, and a small value. And again, I think I'm seeing offsets and sizes. So these offsets and sizes seem to carry on all the way to this point, which is at 6,080. I remember that number. So this looks like a table with offsets and sizes for things. No idea what kind of things, but this looks like some kind of an offset. We have up to 6,080. We have like an 80 hex byte header. So we have 6,000 hex bytes divided by 8 is C00, or 3,072. I've seen that number. It's right here. This was all the way in the top bit. Just after the 1A's, we had C00 in little endian. So this looks like the amount of entries in the file. We have an index. We know how big the index is. We know how many entries we have. We can read this. Just to double check. If we try to read all the way to the end of the file, does that work? So we take the last couple of entries, and that gets us to an offset of 40AB4. And looking at this, I have 40AB0, and that line has 4 bytes. So I think this maps the entire file. We figured out the entire file structure, and we can read them. So now we can read everything that is in an FLX file. Turns out file extensions didn't mean anything to the developers, because there's a whole bunch of DAP files that have the same file format. Oh, all right, that means we have 4 more that we can read. And we can take that, we write a bit of code. It does all of this, it does all the checking that we are actually correct, and it will just blow up if we're wrong somewhere. So if we made a wrong assumption, we'll know, but we can read bits. And then we have a bunch of chunks of an FLX file. Now we'll go and figure out what that is. So this is a different file, and we'll try to figure out what we can see. Again, does anybody see a kind of pattern? What kind of pattern do you see?
03002084.
Yes.
On the next line, shifting, and again, shifting.
Yes. Which means that you're looking at the actual values. I was trying to go for the primordial brain approach. If I'm looking at this and not even understanding what I'm seeing, I see some diagonal lines. And if you're seeing this kind of diagonal line, it usually means you have some kind of a fixed size thing. It doesn't need to be like this. It could be a bit different slant, but usually this means it's some kind of fixed size. And looking at it, between these are 9 bytes. Between these are 9 bytes. Even the ones that wrap around, it's 9 bytes. So I'm guessing we have 9-byte entries. Now, if we shift that over a bit, this is starting to look like a table. So now we can try to find out if any of these have meaning. We can also first check to see if we're actually correct. We think they're 9 bytes each, and the file is 18,000 something bytes, which means we have 2,048 entries. That's a nice round number for developers. There's a different file that has 2,048. It's one of the FLX ones. It's shapes.flx. So this is type info referring to shapes. So I'm guessing there are 2,048 shapes, and this is describing how they should behave, and the shapes are just describing how they look. That looks nice. And each of these turns out to have bitpack type data per shape. Now in Ultima 8, these used to be 8 bytes, so it isn't quite a direct match, but it sort of matches. Then we look at fix.dat. I'm going to be speeding up a little bit. I see I have very little time left. These seem to be 16-byte entries. So what can we see in these? I have a whole bunch of numbers. This looks like little endian 2-byte numbers. And then we have a whole lot of 10s. So I'm guessing 16-byte entries. We'll just see if we can guess a field and figure out what kind of thing it could mean and maybe draw it out on an image to see if it looks like a thing and then gets to that. The first one is the X value, the second one is the Y value, the third one is the Z value. And the fourth one is 10. A bunch of times, but not always. Turns out, they're actually trying to do some compression. So when you have a game level, you typically have a whole lot of conglomerations of things, like a couple of floor tiles that combine to make a bigger floor tile, or you have a small room that's copied all over the level. And they do this compactly by saying there's a copy of a thing, and it's this kind of thing, and you need to look them up in a different file. So it turns out these are called globs. And I remember the name glob. It used to be globs. So we have globs of that, which is also an FLX file, gets out into these bits. And these have a whole bunch of entries that have a 2-byte header, so a number of entries, and 6-byte entries. So if we read these are again X, Y, Z, and a type. So it's like the fixed file, but it's basically just expanding the level. Skipping over this bit a bit, this is, so we are doing this one. This is one of the shapes entries, and shapes should be some kind of drawing thing. And if we can get this, we can check that. You can draw something out, see how it looks. If it looks wrong, our brains are really good at seeing that. If it looks right, we're probably right. So this looks to have 8 things. Putting them in these, this looks like these are offsets and sizes again. We can read files, we can read things. So each of these turns out to be an image, run length encoded image. We did run length encoding before. We have indexes per line, and these indexes result in a bit of data for each line. And these bits of data refer to 7 being skip 7 bytes, or 7 pixels, then take 2 pixels and copy those values over. Then skip the next 7, and so on. Decoding this, we get into this kind of a structure for a 16-wide image. This looks a whole lot of isometric to me, which means that this is probably how it's drawn. We can write that out in a bit of code, write a program, run it on thousands and thousands of things to get thousands and thousands of images, and then see if they look right. Turns out they do. So that's the test code output, and we have images. I've got images for shapes. I have level data and globs that I can decode, but in the end, I can basically decode a whole level. So what if we put that all together? If anything was wrong, we'll see, because things are going to look really weird and really wrong. The more you try to implement it, the more you figure out how your assumptions are correct or how they are not. And trying to do this, in the end, renders some images. And I got lucky. The images are only 32,000 pixels wide. It fits in file formats. So we'll just draw a whole level. And for each of the levels, there's 64 of them, we'll just draw the entire thing and see what's in it. And this is my own code drawing a complete level from the original game. That's right. We got a whole bunch of assumptions and they're correct. The green things turn out to be walls that are invisible. So the game doesn't draw them, but it doesn't let you pass through. And I have a bit of Z-sorting issues over here. It's not the thing we're looking at now. And now we have all the level files, we can look at the other ones, because there are only 15 levels in the game, plus the hub world. But there are 64 level files. What's in them? Turns out a whole bunch of copies of levels that people have tried to modify left or right or some way and decided, well, this one's not going to work, but they didn't clean up behind themselves. And if you remember the one bitmap that we had, the one that was silly, they got more silly. If you were to look at this in-game, your screen would only show about this much, which means you wouldn't be able to recognize what this is. You'd need to make a level editor or this kind of code to see this Easter egg. But there's like 5 copies of this one. So even the people editing the levels didn't know there was a cheese fart on it. Being silly. And then you can go beyond this. You can try to see if there are headers for file formats you recognize. You can usually find zlib. And try to find index, offset, and size pairs, and write programs to check your assumptions. If you're doing this on executables, this might be illegal if you're actually looking into what the executable is doing in some places. Your mileage may vary. Just see if you want to do this. I choose not to. And thanks to Moritz Mechtinkat and Gavin Pugh, who reverse engineered Red Alert and Command & Conquer and got me into figuring out how things work. Thanks to everybody who wrote Crusader originally, and the people at EchoSector who are still keeping up an environment where people who like Crusader games can go and talk about them and see if they can get them running again.